Okay, let's look at a more general inversion method. So we saw in the previous video how to invert a 2 by 2 matrix. Um, for a more general method, if we can use elementary row operations to reduce the augmented matrix AI, so we take our square matrix I, and then next to it we put uh, an identity matrix of the same dimension. So if A is 3 by 3, I would be 3 by 3. And then through elementary row operations, reduce this to the form I. So A is transformed into an identity matrix, and that's the reduced row echelon form. So that's what we've been doing in the past. And then the identity matrix part becomes a matrix B. Then B is equal to the inverse of A. Okay, so I'll work through an example here to show the technique. This is exercise 2.4.2. So again, nothing really new here. Still the reduced row echelon form technique, elementary row operations, but now instead of just having a column to the right of our system matrix A, we actually have another matrix. So in this particular example, the matrix A is 1, 0, minus 1. The second row is 3, 2, 0. And then the last row is minus 1, 1, 0. And then now I augment it with an identity matrix of the same size, 0, 1, 0, 0, 0, 1. Okay. Then now I'm going to reduce by elementary row operations the left-hand portion of this augmented matrix to an identity matrix. Okay, so again, same technique. Let me keep the leading one here in the first row. And I see if I take in row 2 and subtract 3 times row 1, then I'll have a 0 here, minus 3. I'll have a 2, minus 3 there, times a minus 1 will give me a plus 3. I'll have a minus 3 here. I keep the one that's here. It'd be 1 minus 3 times 0, and then 0. And then similarly, to get rid of the minus 1 here, I can just add this row to row 1. And so I'll get 0, 1, minus 1, 1, 0, 1. Okay, so now I've got zeros below the leading 1. Can I squeeze in another result here? So for the next step, I want to just eliminate the leading 1 here. So let me write down the first 2 rows. 1, 0, 0, and 0, 2, 3, minus 3, 1, 0. And then for the last row, again, this is actually 2 combined elementary operations. I'm going to multiply row 3 by 2, and then subtract from it row 2. Okay, so here I'll have 0, 2 times 1 minus 2. Here I'll have minus 2, minus 3. Oops, did I do this right? I think I wrote down row 3. I wrote down the original matrix wrong. So let me go back. In the original problem, it was actually minus 1 here, and then row 3 plus row 1. This would be minus 1. So sorry about that. So actually here now I want to take 2 times row 3 plus row 2. So 0, 0. 2 times a minus 1 would give me a minus 2. 1, 2 plus a minus 3 is a -1, and then 0 plus 1, and then this would be 2. So 0, 0, 1, -1, 1, 2. I'm comparing with my notes that I worked out previously. So that looks right. Okay. Now I want to eliminate the non-zero. So here in front and above and below this leading term, I've got all zeros. Above and below this leading term, I've got all zeros. I want to get zeros above and below this leading term. So I see what I can do here is actually subtract add row 3 to row 1. 1 plus a -1 would give me 0 there. So that's going to give me 1, 0, 0. 1 plus 0, 0 plus 0, -1 plus 1. 1 plus a -1 is 0, 0 plus 1, and 0 plus 2. Yeah, so that looks good. And for this row, I want to subtract 3 times row 3. That would force a 0 there. So I'll have 0 minus 0, 2 minus 3 times 0, 3 minus 3 times 1, and then let's see, -3 plus 3, so that gives me a 0. 1 minus 3 is -2, and then finally here I'll have 0 minus 6, and I'm not going to do anything, don't have to do anything to the last row. -1, 1, 2. So almost there. The only step that's remaining is actually dividing the middle row by 2. 1, 0, 0. I'm going to put a little bar here to separate the two halves. 0, 1, 2, 0, 1, 0, 0, -1, -3. Here I'm just dividing row 2 by 2. And then finally 0, 0, 1, -1, 1, 2. So this is now in the form I, and then this is actually A inverse. So A inverse in this case is 0, 1, 2, 0, -1, -3, -1, 1, 2. Okay. Again, as a check, there's a bit of work here. Not that much more involved than what we've done in the past with reducing a matrix to reduced row echelon form, except now with instead of just having a single column here, we've got multiple rows. Again, the number of rows would be multiple columns. The number of columns would be equal to the number of columns in A. So if A is 4 by 4, the identity matrix would be 4 by 4. You can check your results again in Octave, and I encourage you to do that. Okay, using the reduced row echelon form function RREF, and then we can form the augmented matrix by you have to use square brackets to form a new matrix, and then here. A is our matrix that we want to find the inverse of, and then the function EYI actually will give you an identity matrix. Here we could use 3 by 3 or 4 by 4, 4. Actually, we want to form an identity matrix that's exactly the same size as A. So this would do that. This would form an identity matrix that's exactly the same size as our A matrix. Then close the bracket. So this gives us a new matrix, which is an augmented matrix. We've augmented A with identity matrix, and then close the parenthesis. And then the result here would be you'll get back a matrix result where the left-hand side will be I, and then on the right-hand side of the matrix the last half of the columns then would form A inverse. And so you could check your elementary row operation method technique by actually using octave. And again, I'd recommend that you do that. Okay. So actually, we've been concentrating on linear systems, solving linear systems of equations. So let's go back and revisit that problem. Now that we've got this new tool, okay. So for a system of n equations and n unknowns, and so now this is a more restrictive problem. It has to be a square system with the same number of equations as unknowns, and we put that restriction on here because the inverse of a non-square matrix does not exist. So it's this n equations and n unknowns that results in a system matrix A that's square or n by n. Okay. So, and then here was the problem. We've seen how we can express a linear system of equations in matrix form like this. Now, if A inverse exists, the unique, the one and only solution is X is A inverse times B. Okay. Now, a couple of notes. If A inverse does not exist, the system may be inconsistent, or it may have an infinite number of solutions. We don't know. It's only if A inverse exists, then we know that the system falls into that case where there is only one solution. Okay. Also note here that to find the solution, we left multiply B by A inverse. Okay. So again, an easy reminder of that is actually to go through the work. Here on the left-hand side, we have A times X is equal to B. Well, I need to left multiply both sides of this equation so that I get an A minus A term. Okay, left multiply both sides. If I right multiply both sides, I'm going to have A X bar A inverse, which doesn't reduce. Okay, I have to get the A inverse and A next to each other. Okay, so then the next step here is A inverse A is equal to I, the identity matrix, but I times X is equal to X. So I'm left with, the result. If I, right multiplied, actually, again, it doesn't give me the correct answer. In fact, that if I right multiply here, that multiplication is not even defined because B is an n by 1 vector. So I can left multiply by an n by n matrix and get an n by 1 result. But if I right multiply, B and A or A inverse aren't even compatible for multiplication. The same would be true here. A times X is an n by 1 result. So I can't right multiply by an n by n matrix. That's not even compatible for multiplication. Let me just point out, in general, solving a system of equations this way, there are some restrictions. For one, it has to be a square system. The other thing is it does take a bit more work to find a matrix inverse than it does to reduce the augmented matrix to reduce row echelon form. Okay, so in general, the technique we looked at previously is going to be the preferred technique for solving a system of equations. Having said that, there are a couple of cases where you may want to find the inverse matrix. If you think back to when we applied linear systems to our flow networks, the left-hand side here was determined by the structure of the network. The right-hand side were just the constants, the flows into and out of the system. Okay, so if you've got a case where the flow structure does not change, but the inputs and outputs, the constants may change, then it may be worthwhile to find A inverse so that if your inputs and outputs change, if your constants change, you can quickly find a new solution without having to go through the complete process of reducing the augmented matrix AB to reduced row echelon form. So that's one case. In general, again, using the reduced row echelon form method is also going to indicate whether or not a system is inconsistent or whether it has an infinite number of solutions. Using this inverse technique, if A inverse does not exist, we don't know. It could be inconsistent. It could be have an infinite number of solutions. Of course, those are two very different situations, and again, we don't know which is the case by trying to compute A inverse and then just finding it doesn't exist. The reduced row echelon form will tell us that. Having said that, though, the concept of an inverse of a matrix is very important in linear algebra. Indeed, we'll use the concept of a matrix inverse to solve a lot of matrix algebra problems. Okay, and we'll see that in the homework for today, as well as in the future as we look at additional topics in linear algebra. And that concludes today, not today's lecture, but this video on where we covered a general matrix inversion technique and then also linear systems. Again, and there's another video today where we'll actually look at some properties of the matrix inverse. So stay tuned.